Hello everyone, let's talk about the binary search trees. First of all, a binary search tree is a binary tree. Every node has at most two descendants, maybe no descendants, in which case it is a leaf, or it can have one descendant, but no more than two. Second, the values in those nodes, the actual information, is stored in a certain order. That is, if the child is on the left, it has smaller value than the parent. If the child is on the right, it has higher value than the parent. And we would like to build these trees. We would like to add elements to it. Say, starting from an empty tree start, you can add elements to it. And you can, if you like, for example, you can put a new element in the tree while respecting these rules about left and right. Left smaller, right larger. Now let us try to add 7 to this tree. Well, in the root there is 8, I have to go left. Here it's 4, 7 is bigger than 4, so I have to go right. And 5 is smaller than 7, so I have to go right again. And here goes my 7. This is a new node that I created by following these rules. Now let us add 10 now. Add 10. 10 is bigger than 8, I have to go to the right. 10 is bigger than 9, so I have to go to the right again. But it is less than 11, so here I have to go to the left. So 10 will look like this. And there is still nothing here, and nothing here. I draw these arrows with nothing so that you can see that each of these objects, information with 2 descendants, is a node, and that's the first thing that we will have to create. So we want to add, to create trees like that, and also we want to print the values in order. So printing the values in order. How would we do that? First of all, go to the leftmost every time you can until the next one is nil. This is the smallest that you will get there. Then back up by 1 and print the previous one, after which you have to go and check all the ones on the right of the 4. So this is 5. Then try going to the left to get maybe a smaller value. Maybe there was a 6 here, but there is nothing, so go to the 7. Now back up all the way to as far as you have been. So now I'm printing 8, and I'm continuing in this fashion. Alright, so let's make it happen. So far I have a little bit of a starter code here. So this is a class node. It has integer info and 2 nodes for left and for right. And this is a constructor for the node. It instantiates the left and the right as null, and then we will need to tag on children to this tree as they come up. And I'm kind of trying to recreate, oops, that is wrong, and that is unnecessary. So I'd like to create a tree according to these rules. So let me pick up my scheme and tree dot add 4 and then add 3, add 5, and add 9, add 11. Alright, so this will be my testing code. So now it's time to, first of all, we need to define a variable to point at the root of the tree. So it will be an instance of node. And second, we need a constructor for it. Here is a constructor. Let's start from empty one. Okay, and now I need to create a public class, public void add. And what I want to add is just another integer, new int. Alright, let's add things. First of all, if root is null, that is the tree is empty, we would like to add right away, but maybe I need a node variable and just create this to begin with and then figure out where to add it. New node, and there will be a new int there. Okay, if root, I need parentheses, root equals to null, then what I do is just say that root equals to new node. And that's all to it. And now, while root, so we can assume at this point that the root is not null. I don't want to redefine the variable root because I don't want to lose the root of my tree. So I need another node variable, current equals to root initially, and now I need to go down this tree in the appropriate way, whether it's less or more, whether it is bigger or smaller. Because 7 is less than 8, I first go to the left, and since 7 is bigger than 4, I go to the right, and since it's bigger than 5, I go to the right, and finally I found my spot to put the 7 in. So always the new elements will go into the leaves. Okay, so that's what we want to do. And there should be a while loop that will be dealing with the moving of my current node left or right, depending on the value. So maybe I want a variable done, like a flag variable, boolean equals to false, boolean done equals false, equals false, and while not done, or just break the loop. Breaking the loop is probably better when we need it. So while true, something is off here. I just did not close the parentheses. Okay, the brace. While true, if current dot info is less than new int, then we move to the left. move to the left. Actually, no, then we move to the right. If current dot next dot right is not null, current dot right is not null, then we move. Then we say current equals to current dot right. And in the other case, we actually say that current dot right equals to new node. So that case is done when current info is less than uint. In one case we moved, that is if the right was not null, we have to move to that and then repeat. And else if the other way around, we have to do the same from the left. We have to do the same from the left, and else, that is the case when they are equal. That's what we will say. System dot out dot println the value is already on the list, in the tree, sorry. So we don't allow the duplicate. Okay. New node left. And in case we actually did this, we should say break so that the loop breaks. And in this case, break. Okay, so we broke our loop whenever, no. Yeah, in this case we broke, and in this case we broke. Okay. So let's see if this works. We cannot see anything because we don't have a way of printing values. Okay, we are in an infinite loop now because I did not say break, and there is some repetition apparently. No, there is no repetition. Okay, so let's think this through again. So if root just add, so while true we were getting else case, if current less, if it is greater, then we move to left. Left, else, new node, break. Else, and in this case we should also break, but that doesn't sound right because we should never have been in this case. While true, if current dot info. Okay, there is an else here missing. Else be, nope. So if this, then that, else this. Let me close it so that you can see more of the code. So current is true, while true, do this, or that, or value is already there, and let us see how it goes now. So we cannot technically see anything if we did it right. Okay. So the next thing, after the add function, we need to have a way of printing. And as I was saying previously, just to remind ourselves what we're doing, I want to prioritize the left, so I want to prioritize them smallest. So first of all, the way we print will be recursive. Yeah, I think I want it to be recursive. So first of all, it drills down to the leftmost entry, which will be the smallest. Then it backs up and does the previous one. Then it has to choose check the right one. And each time we will call the function itself. So we will treat this like a subtree, like a tree in its own right. Okay, I think that's a plan. So let's do this. Public void print, and I have to pass the node into it. Node root 1. So this is a relative root because we are going to write a recursive function. This is a relative root, and now that I think about it, I don't have to have an instance here. So public static void print. I'm not using the root there, so I'm starting from whichever I'm assigning to be a root. Okay. So if root is null, we don't do anything. So while root 1 is not null. Actually, I don't need a while. If root 1 is not null, I will first of all check the left entry. If root 1 dot left is not null, not equal to null, then I will go there. And by going there, I mean recursive call. Print root 1. Root 1 left. So this will drill down all the way. And finally, at some point, there is no root 1 left. That is, root 1 dot left is equal to null. This is when we actually print the root 1 dot info, or what it was, info. So we need to print that. should say system dot out println. And after that, we need to check. Actually, this is actually no, that's okay. Similarly, after that, we are going to check the right way of going, the right path. So root1 right is not null. That is going to the bigger values than the value in this relative root. Then I have to print all the right subtree. Okay. So first it checks the left subtree. If there is a left subtree, it goes in there. Eventually there is none. That is the moment when root1 info is printed, and then we are going to check the right tree with the same priority. And now that we have print tree dot print, and oh, sorry, that has to be a class name. Binary search tree print tree. Tree dot root. I should get get a getter to be appropriate, but let's see how it prints. Alright, so it prints all the values currently that we added in increasing order. That is how we designed it. So this choice with the left for smaller, right for bigger allows us to store values, and in order to print those values in order, we are just prioritizing the left first. So this is prioritizing the left. And the last but not least, you can ask me, now where is the search? And the search is actually right here. The same thing as we used for add can be quickly modified to use for, could be quickly and immediately modified for search. You just have to remove certain lines and change the printed outcome. So the value is already in the tree, or if it ran around the tree and did not find the value, it did not, it was not on the tree. So this is kind of almost your purpose. You can also tell if the value is in the tree already. Okay, and going back to the general ideas, why is this a good thing? Now notice that you can store a lot of values with a very small depth of the tree. Now that is something I'd like to pay some attention to. Suppose, for sake of the argument, that your tree is like complete of up to a certain level, there are no missing values. See, I have to kind of draw much tighter now because there is so many more of them. On this level there is 1, 2, 4, 8, there will be 16. In general, if this is 0 level, level 0, 1, 2, 3, 4, this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and so on. So a complete tree of height n, or height h, will have about 2 to the power h plus 1 elements. So to store 1000 elements, you have to only go like 10 or 11 deep. Actually, 9. You only have to go 9 deep. And this is a small depth. So in order to do a search using these rules, left for smaller, right for larger, you have to move around only up to the depth. Up to the depth of this tree, which means making like for 1000 elements, it means making h moves. In general, depth of the tree is related to its to the number of elements with it logarithmically. So elements. In other words, h is like log base 2 of n minus 1, and I have to take in general the tree is not always complete, so I would have to take a ceiling. So you can store a lot of elements in the tree that is not that deep, and to search for it you only have to go up to the height of this tree, which isn't a lot, which is logarithmic complexity. That will something that we will talk about later in data structures. And that's what makes it so efficient. If you spend time building this tree correctly, then searching through it through n elements will take only logarithm of n sort of moves. Okay, so this is almost like all basics that you need to know about binary search tree, except for a slightly bigger one: how to balance it. So a word of warning, why I was sort of lying to you a little bit. And oops, I was lying to you a little bit. So under some conditions, your tree may just look like that. For example, if you were adding smaller and smaller numbers, and this tree obviously loses all the benefits of being the tree, like it's missing all the other branches, right? So it's like a list all over again. So there is a procedure how to deal with like deep trees which have very few branches and turn them into balanced trees which have which have a lot of branches and which are shallow. And that is called balancing. Feel free to read about it. We will not cover it here.